So what I haven't explained yet is how does CUR select which rows and which columns to fit into the matrix C or into the matrix R. And here's the algorithm to do this. We call this algorithm the column select algorithm. I'll first just explain how do we select a set of columns. So the idea is the following, right? We are given the matrix A. It's some real valued matrix with m rows and n columns, and we want to select a set of C columns from our data. And the way we will do this is the following. First, what we do is we will go and for every we will compute for every column x, we will compute its Frobenius norm, right? So kind of its length, and we will divide that by the total length of all the columns. So in some sense, we are just asking how long is this column with respect to the length of all other columns. And this now defines us a probability distribution, right? Where long columns where the sum of the squared errors is big, will have a higher p of x, and then columns where their sum of squared values is small, they will also have small p of x, okay? So this is now we basically compute a probability distribution over the columns. And now what do we do in the steps 3 to 5 is basically we have a for loop from 1 up to the C, where C is the number of columns we want to select. And what we do is we pick a column J with probability proportional to the length of that column. And once we select the column, we put it in the matrix C by taking it out and multiplying it with a square root of C times the probability for that column being chosen. Okay? So what does this basically mean is the following. It means that all we need to do to select the columns is that we need to compute the length of every column, and then we need to select C columns out of our matrix, where the probability of selecting a column is proportional to the sum of the squares of the entries in that column. What is important to note here is that the same column can be selected multiple times, right? So every time we select the columns independently from the matrix. So the same column can be sampled multiple times. The algorithm very nicely generalizes to rows. Everything is the same. So basically now we compute the length of every row, create a probability distribution over the lengths, and now pick the row proportional to its length and put it into our matrix R. And we do this, in this case, little r times, and we are done. So now that we have C and R created, the question is how do we compute matrix U? And the way we will compute matrix U is first we will define the matrix W to be the intersection of rows and columns that we sampled, right? So if I think of my columns C and my row matrix R, so this is C and this is R, then what is matrix W is basically the intersection of these rows, right? So I will only take rows and columns that appear both in C and R, and this will generate me the matrix W. And then what I will do is I will perform the SVD of matrix W. This is called, right? So I have W and I will perform SVD on it. I know I can do this and I can do it uniquely. So I will think that I'm getting matrix X, the singular value matrix Z, and the matrix Y transpose. And then I will compute the matrix U, which is called the Moore-Penrose pseudo-inverse, right? And the way I do this is basically the mathematical symbol for this is that I take my matrix W and I want to compute this pseudo-inverse, so I denote that as W plus. And the way I do this is I compute this by taking my matrix Y, multiplying it with Z plus times X transpose, where the matrix of Z plus is simply the reciprocal values of non-zero singular values, right? So if a singular value in my matrix Z is non-zero, then Z plus is simply 1 over that singular value that I have there that is non-zero. And if the singular value is 0, then I just leave the whole thing at the 0. And this is called the pseudo-inverse, right? And now basically we have everything we need. We took the intersection of C and R, computed this pseudo-inverse, where basically we took the SVD of the intersection, took the 1 over the singular values, multiplied everything together, and we obtained our matrix U. So now we have the complete CUR decomposition. Just to give you an example kind of more concretely, I had a very kind of theoretical theorem or a very theoretical statement before. Here is a statement that's kind of easier to think about, right? So imagine the following. Imagine that I'm given my matrix A. I sample C columns where C is of order k times log k divided by some little epsilon squared. I also select R rows where R is k log k divided by epsilon squared, right? So I sample columns, I sample rows, I compute my U to be the pseudo inverse of the W of the intersection. Then what turns out is that the reconstruction error of CUR is less than twice than 2 plus epsilon times the reconstruction error of SVD, right? This is the SVD with probability 89%, right? So basically the theorem I had before, now I simplified it, putting in some numbers. And basically what this means is that SVD picks k singular vectors, CUR will pick k log k, so kind of just a bit more than k. And this means that its reconstruction error will be better, or at worst will be 2 times worse than that of SVD, and that will happen with probability 98%, right? So we get near optimal, right, kind of at most twice as bad as SVD, almost always, which is a great result.